The talk is called Hacking Medical Devices for Fun and Insulin, Breaking the Human SCADA System. Please give a warm welcome to Jay Radckiffe.
Hello? Excellent. Thank you, everybody, for coming. Today we're going to be talking about medical devices, specifically about insulin pumps. And the first part of the discussion is going to be about the background of diabetes, so it's going to be a little bit medical in nature to help everybody kind of understand the impacts of what these medical devices do, and if they can be exploited, what impacts they would have on a human being. And we're going to talk about a couple of the medical devices that I personally own that I've done the research on. But let's talk a little bit about how we got here, okay? And the idea here is, can evil people hack medical devices? Can hackers get into medical devices and do bad things? And I was working on this presentation, and I have a 5-year-old son. He comes up to me and he says, "What you working on, Dad?" I said, "Well, I'm working on a presentation about my little medical device," because he knows that I have an insulin pump and it gives me medicine all the time. And I said, "I want to show that bad people can't do things to Dad with that medical device." And he goes, "You mean bad people like Dr. Doofenshmirtz?" I said, "Well, I wouldn't be too worried about him, but yeah." So then my son went on and on about creating this innator, and he was going to come after me, and he was going to render me dead. And that's pretty much what we're going to talk about today, is the feasibility of this. And at the end, I'm going to be doing a demonstration that shows that I can turn off insulin pumps remotely, or a particular insulin pump remotely. So why diabetic devices? Well, on my 22nd birthday, I was diagnosed with diabetes. I had lost 40 pounds in about a month and a half, and I had an extreme thirst that could not be quenched. 5-6 gallons of fluids a day, no problem. And from that time, I've taken insulin to help me with my condition, and furthering that, I've gotten a collection of medical devices that are attached to me at all times to help me with my condition. And these devices have all kinds of wireless features, and they do all kinds of neat things. 2 years ago, I was at a talk at DEF CON on parking meter hacking. And a good friend of mine was sitting next to me who's also a diabetic, and he goes, I was talking with him, and he was like, "Wouldn't it be a good idea if we did a presentation, on our medical devices and see what kind of things we could do with them?" And I thought, that's a great idea. I should do that. So I got around to it this year. I've spent the last 4.5 months of my personal time after work working on this, on basically a shoestring budget, to see what the possibilities are of that. Now, how does diabetes work? Well, a person without diabetes typically has a blood sugar between 90 and 120. And your liver and your pancreas work together to control these levels. So your liver will give you some sugar to raise that up, and your pancreas will give insulin to lower it. And the pancreas produces this insulin, which binds with the sugar and allows it to be used for energy. So you could use that energy up if you decide to take a walk or go running, or if you decide to sit in front of your computer and browse the internet. It will convert that into fat, and it will store that energy for use later. And the liver takes some of that sugar and puts it in reserve. Okay, so if you go a long time without eating, your liver will give you some sugar so you can keep running. Now, with a type 1 diabetic, which used to be called juvenile diabetes, is when a person loses this ability to produce insulin at all. The pancreas just stops producing it. And they don't really know why it does that. It's still being studied and talked about quite a bit, but the point is that it goes away. So rather than the pancreas producing insulin, the person has to administer a synthetic insulin as a replacement. Right? They could do that through a syringe multiple times a day. They can also do it with an insulin pump. Now, that sounds really simple to just replace the insulin, but there's an infinite number of variables that you have to consider that use to equate how much insulin you need to take. That could be stress, time of day, physical activity, illness, how much fiber's in the food, how much fat's in the food, and all of these play a factor in how much insulin a person needs to give themselves. And it's all very customized to each individual. So In a normal person's sugar relationship, they can eat a Snickers bar, which like says has 32 grams of carbohydrates. Now, as that sugar enters your bloodstream, the pancreas will start to produce insulin and release it. That's going to match the quantity of that sugar to allow the conversion of that Snickers bar into energy. And your sugar levels might jump up a little bit, 10, 20 points, as the insulin takes effect, but typically you don't see that much of a spike. Now, an abnormal sugar relationship, a person with diabetes eats that same candy bar, and then they have to give themselves insulin to cover the amount of carbohydrates in that, okay? So for example, if you have to take 1 unit of insulin for 10 grams of carbohydrates, you'd give yourself 3 units of insulin here. Now, ideally, you give insulin at the perfect time, so it mimics the human insulin, keeping those sugar levels stable. That almost never happens, right? But let's say I give myself no insulin. I eat the Snickers bar, and I'm like, meh, whatever. I don't need the insulin. In that case, my sugar is going to go and have a huge spike, over 200 points in my case, within about 40 minutes. And that sugar can't be processed into energy. And so the body reacts in 2 ways. The first is that it filters that sugar out through the kidneys. This is stressful to the kidneys. It leads you to be very, very thirsty because you need fluids to flush all that sugar out of your body. The second thing that occurs is your body switches to fat for energy. And if the body uses purely fat for energy, it produces, in the metabolism process, produces what are called ketones. And you can go into ketosis or ketoacidosis, which is a harmful condition where your body chemistry gets all out of whack, and it usually ends up leading to a hospital visit. Some of the symptoms of having really high blood sugar would be headaches, you get blurry vision. If you have high blood sugar for a very long time, like years, you can have long-term kidney damage. Now let's say I give myself too much insulin, right? Let's say I eat that Snickers bar and I give myself, instead of 3 units, I give myself 6 units. Now we have a much bigger problem because the heart and the brain only run on sugar. So when you start to dip below 60, your body starts shutting things down. And it starts from the outside and comes inside. So you might start to lose fine motor control. Your hands will start to shake, right? Because your body's conserving the available energy for the important things, respiratory system and your heart, right? So you start sweating, you lose fine motor control. The way I describe it is basically like, you know when you might know this condition from last night. You drank way too much. You're drunk, right? And you're on the edge of blacking out because you drank way too much, right? It's the same feeling. The problem is that none of the fun parts. You just instantly go to that horrible part at the end. And the even scarier part is when you're overly drunk, you can close your eyes and go, I'm just going to pass out and wake up in the morning with a horrible hangover. In this case, as a diabetic, when you feel like you're going to pass out, you could end up in a hospital in a coma. And if you don't take action to increase your blood sugar, you could have respiratory failure and death. So it's a very serious condition when your blood sugar goes too low. And some diabetics even lose the ability to feel these symptoms. They go instantaneously to like 40, 30 before they start to react. They lose that shaking feeling, the tremors in their hands, the precursor that lets you know, hey, my blood sugar is way too low, you got to do something. In many ways, I kind of think of this like a human chemical plant, right? The body is producing all these chemicals to kind of keep these levels stable. And I've done a lot of research on SCADA systems in my professional work, and I saw a lot of similarities, right? So there's a relationship between pressure and the temperature of chemicals, just like insulin and sugar, right? And the SCADA system would monitor the pressure and add or remove heat to keep that pressure constant. If the pressure gets too high, the temperature gets too high, you could have an explosion. If it gets too low, you might have a failure, like a water delivery system. It could stop delivering water. So you want to try and balance those sugar levels and the amount of insulin to keep it within that range, just like you would at a chemical plant, try to keep those chemicals stable in those environments. So here's a graph of my blood sugar on a really good day. We start off right in this blue zone, which is 90 to 120, 130, which is where I always want to be. And you could see right at about 7 a.m. I had breakfast, and I have a huge blood sugar spike, right? I probably had pancakes, something real sugary, maybe a donut. I have no idea. I don't remember what I had. But then you could see the insulin kick in, and that blood sugar drops right back down into a normal range. I have lunch, it goes up a little bit, back down to safe zone, up a little bit, back down to safe after dinner. That's a really good day. Would love to have this day every day. This is a bad day, okay? Start off in the morning, hypoglycemic. My blood sugar is way too low. I'm shaky. I probably feel like crap. Have some orange juice, have some breakfast, and you see, I obviously didn't give myself insulin because I have a huge spike all the way up to 400, right? Then what happens? I gave myself way too much insulin to try and correct that condition from before, and I completely crash at dinner, right back down to 50. Then I have dinner. Obviously, I gave myself no insulin then because back up to 400 within an hour. This is a bad day, and this is what diabetics have to deal with every day, every meal that they have to eat. They have to think about, what's my blood sugar? Where is it going to go? What kind of food is it? I have to remember to give myself the medicine. You can see this kind of condition repeats over and over again. You have good days, you have bad days. So how do we adjust those levels? We talked about a water plant or a chemical plant. Diabetics monitor their pressure levels, their sugar levels, and adjust insulin and food to control those levels. If your blood sugar is too low, you might drink some fruit juice or some other sugary foods. But it's really hard to precisely measure the amount of carbohydrates you need to get yourself right back into the zone, right? Like, for example, I'm petrified that I'm going to go low during this speech, so I had them bring me some pop, and this has like 32 grams, 40 grams of carbohydrates. So if I drink this whole thing, within an hour, I'm at 250, right? That's too much sugar to take, but how do you control that? It's difficult. It also could take time to get that sugar in. It's not instantaneous. I could sit down and drink that, and I'm still going to feel like crap for at least 15 minutes, if not longer. And my body wants to eat. It wants to drink all that and then 3 more because it's desperate for sugar. What happens when my sugar is too high? So this is a harder one to deal with because insulin lasts 3 to 4 hours, and it can't be removed, and it can't be adjusted. So I have to wait for it to act, and I have to wait for it to get out of my system. So if I'm high, I have a choice. I can give myself more insulin, or I can just wait and see where I land, right? And this is a never-ending manual process that people who are diabetic go through over and over again. So let's get to the technology. First one we're going to talk about is continuous glucose monitors. It's a newer technology that's come out. It's a small wire that goes into your tissue, and it measures fluid that's in between your layers of tissues. And what it does is it graphs the sugar values over time. And it's a big leap forward compared to the other technologies. Let's talk about the history of how we measure our sugar, right? Pre-technology, they used to taste urine. You would go to the doctor, and they would actually taste the urine. This is gross, and it's very imprecise, right? And at the time, it really had no impact, right? Okay, you're a diabetic. We don't have synthetic insulin at this point yet. So that just pretty much means you're going to die early. In the early 80s, they started coming out with a home test kit. Now, if you know somebody who's a diabetic or have been around a diabetic, you've probably seen them take their blood sugar, right? They get a little strip out, put it in this machine, they poke their finger, get a little drop of blood, put it on the test strip, and then you get a sugar value 5-10 seconds later, right? Those strips cost about 75 cents to $1.25 each. Typical diabetic might test anywhere between 2 times a day and 10 times a day. You can see the cost build up real quick. There's also problems with this, right? It's just a data point. When you take your sugar, you don't know what the direction it's going. Are you going down real fast? Are you going up real fast? What was your blood sugar 2 hours ago? You have no idea. You just know that point in time. This method right here is still the most commonly used method that diabetics test their sugar on. Mid-2000s, continuous glucose meters come out. And what this does is it measures the resistive value of that fluid in your tissue. And what they found is that as your blood sugar got up, the conductivity of that fluid went up. So you measure that resistive value, and you could gauge what your blood sugar's at. What they do is they attach a little wireless sensor into your tissue. It lasts for 7 days, and every 5 minutes, it beacons out what that electrical value is. Right? You still need to do a calibration, right? Every 12 hours, it wants to make sure that that electrical number lines up with the right blood sugar number, right? And those sensors cost between $40 and $70 each, and they last, per FDA regulations, a week. A lot of diabetics I know wear them 14, 15, to get as much time as they can, because a lot of time insurance won't pay for these. And this is kind of what it looks like. You've got a sensor that attaches usually to your midsection, and then a little pager-like device that has a chart that shows you your current blood sugar and what the past 6, 10, 24 hours are. You can see that this technology is kind of fraught when you look at this chart that I showed you earlier. You see, there's big gaps in that data. And that's at a time where the receiver just didn't hear the beacon. So you could see that this technology isn't quite perfect. And you can also see, how does this, I'm thinking to myself, how does this wireless transmission stuff work? I got to thinking about it more, and I came kind of a little hypothesis. And I'm thinking, these CGM wireless results are got to be transmitted with little to no security concerns, right? They've got to be vulnerable somehow. And here's the foundation of that, right? Those little sensors, they run on a 1.5 volt watch battery, and they last for 2 years. Any kind of cryptography would require a little bit more horsepower from just a power draw perspective. We're talking about over 200,000 transmits in the lifespan of that sensor. I'm also thinking it's not bidirectional. And the reason is the sensor is just a little tiny thing that you clip into this plastic, the plastic receiver. It has no ability to tell it time, has no ability to tell it what receiving unit it's supposed to be sending the data to. It's unaware of any of those things. You don't set a sequence number or say, hey, start now, or reset it. It has none of that. So I'm thinking probably unidirectional communication, like a UDP packet. But how do we verify this? How do I go about grabbing this data and looking at the transmission? Well, I got to do a little recon work first. I got to do a little research. So the first thing I did, oddly, was read the manual. And actually, this was the biggest wealth of information that I could have. The FCC requires that you disclose a bunch of information. So you can see in the manual here, it tells me what frequency it's on, tells me the bandwidth, how much power it's transmitting with, the modulation type. It even tells me how big the packet is. And it tells me it's 9 milliseconds, and it happens every 5 minutes. So I'm a ham radio operator, and it just so happens that my radios can receive on the frequency this transmits on. And I was like, I wonder what that sounds like. And it sounds like this. That little chirp is a 9 millisecond transmission from my sensor. What I have to do now is figure out a way to capture that little chirp, break it down into binary so I can read it. So I look at the FCC documents. Now, all RF transmitting devices go through FCC testing and verification. And the FCC issues a transmitter ID for any device. You look on your cell phone, you look at pretty much any piece of technology you have, it probably has one on it. If you go to this website, you put in that transmitter ID, you get a very detailed report, right? It's got screen captures from spectrum analyzers and oscilloscopes and just a wealth of data from equipment that I could never afford to buy and most companies can't afford to buy. That was tremendously helpful in looking at how that signal is transmitted and what type of technology I need to look at to get that transmitted signal. I also went and looked at the patent that the company does. And when a company files a patent, it has to disclose everything about that device, how it's made, how it works. It's basically they give up the right to keep that a secret. That's what they do in a patent. So I go to this website, I looked for the specific manufacturer, and I found their patent report. And it gave me another wealth of information about how those devices are made, how they work, lots of block diagrams that gave up a lot of information. I also took the receiving unit apart. You could see the chip here, and you can also see, I have a laser pointer, but I can't get to it. On the bottom side there, all along that curve at the bottom, that's the receiving antenna, and it went all the way around that circuit board, right? And I also found out that this chip had a part number. Excellent, right? Oh, it's out of production. I went and found the company. They were bought by somebody else, and I tried to find the engineer that made the chip, and he had left the company. But they archived those data sheets. I looked at the data sheet to find out what kind of information I could get. And it turns out that these chips are also used in SCADA environments, industrial control settings. These are wireless chips that are going to be used in chemical plants on wireless transmitting sensors. Maybe they measure pressure. They could be used in a wide variety of things. So the first place I went to capture this transmission was an Arduino board. And that's a little hardware board that you can use, that you plug in sensors and different modules, and you can communicate with them with basically a programming language. These have become very, very popular. You've probably seen some talks on it here, and probably see some talks on it over the weekend at DEF CON. There's two RF modules that I looked at to use with this Arduino board, an RFM22 and a CC1101 by Texas Instruments. Both of these boards, less than $10 on eBay. Very easy to get. And it covers a big spectrum, anything from 300 megahertz to 900 megahertz. It's got a little external antenna on the top of it, so I can make a big antenna and listen far away or transmit far away. This worked out really well. I'm like, this is going to be cake, no problem. Not so much, right? First, this little board is tricky to program. They have all these register settings that control the RF deck and how it's going to receive. And they all have to be set, and they're all defaulted to some value that really doesn't work. For an example, I'll give you one example here. Register number 8 is packet control register, and there are 8 bits of data in that register. Here's the manual page for that particular register. I got data whitening. I've got the format of the receiving and transmitting data, the CRC calculation, is it used, is it not used, how long the packet is. I've got all these things I got to configure. There are over 100 registers. So I've got to dig through and figure out what the right register value is, pretty much by trial and error. Here's another problem. That even after you determine the register setting, you've got to set them. And there's no verification step to that, right? I lost a couple weeks to this problem. I thought I was writing the value to the register. It turns out I wasn't changing the value of the register. There is no indication at all. You know, if you set a variable and you try and give it something that it's not supposed to have, the processor balks at you and is like, you can't do that. That's crazy. It doesn't happen in hardware, right? And this is the first real difference that I figured out between working on computer systems and working in hardware. Hardware is very concerned with CPU cycles. So much of the hardware code I looked at in this entire process had no verification of its action. It just did whatever it was told, without checking boundaries, without checking what type of data you're putting into that variable. If I did try to do that with a Perl program or a shell script or any modern programming language, I would have gotten an error. But I also started to think, right? Where have I seen this before? We see a lot of exploits and vulnerabilities based on the concept here, right? Buffer overflows due to not verifying boundaries in string copy. So could we see this maybe in hardware now? If we start doing more hardware hacking and nobody's checking boundaries because it takes more CPU cycles, because you're concerned about that in these embedded hardware devices, are there going to be buffer overflows in the hardware? I think that could be a good case. And based upon the code that I saw, I think we are going to see more of that. So let's talk a little bit about the modulation type of this RF. It's called on-off keying. It's also notated as OOK. And it's the simplest form of modulation, right? It's purely binary. No signal is a 0. You have signal, it's a 1. It moves very fast, right? A little over 8,000 bits a second, 9 millisecond transmission, 76 bits. You can see a little up there how that would work. Next problem I run into is the RF module, these registers, are starting to ask me questions that I have no clue, and I haven't seen anything in any of the recon work I did about this, right? First one is called a preamble. This is a series of binary 1s and 0s, so it would be 1 0, 1 0, 1 0, 1 0. And it's used to indicate that to the receiver to tell it, hey, you need to wake up out of your power saving mode, and you need to adjust your gain settings to make sure you receive the signal properly. I have no idea if this thing uses a preamble or how long that preamble is. And the register values go anywhere between like 8 bits and 64 bits. And I'm thinking to myself, 64 bits, this thing only transmits 76 bits. It's definitely not that big. So I'm like, I have no idea. Second thing it's asking me for is something called a sync word. Now think of this as like a secret word that you would use to communicate with somebody, right? It's a set of characters that assures that the transmission format is correct. So if you don't receive the secret word, either this transmission's not for me or the transmission has no integrity. It's also asking me for CRC type and location. And this is usually 8 bits. A lot of times it's longer now, but in hardware I've seen it a lot as 8 bits that are at the end of the transmission, and that's used to verify the data integrity in the packet. It's like a checksum that you run, make sure that you got the data correctly. This is kind of what I was expecting to see, right? There's a little preamble, testing, and then there's a sync word, let's say 31337, and then a bunch of data, and then the CRC at the end, right? So if the receiver doesn't get that 31337 when it decodes that transmission, it throws it away. If it doesn't get 15 when it calculates the CRC in this case, it throws it away. But you know what? No idea the format. None. The data sheet for the chip doesn't mention anything about a preamble, but it does mention a sync word, which is set by the manufacturer in the firmware. So I have no idea. It's not preset. Luckily, I can take this CC1101 module and put it in something called direct mode. Now in direct mode, it's going to spit out 2 signals to an oscilloscope. One is the data, 2 is a clock, right? And that clock acts as a metronome. It gives you an idea of how much time it takes for 1 bit. So you can see here, I've got highlighted a clock, which is 2 clock cycles, and if you look above it, that relates to 2 0 bits. And you can see I've transcribed the rest of this transmission at the top there. 2 1s, 2 0s, a bunch of 1s, 0, 1, 1, and that goes on for the entire transmission. Aha! So now I can decode it. I can see what the transmitter's sending. Maybe I can figure out what the sync word is. So let's talk about what we know about the transmission. 76 bits. I know that the CRC exists because the patent documents mention it, but it doesn't tell me what kind of CRC it is. I know there's a transmitter ID. It's 5 characters long. First character is a 1 or a 0, and the last 4 alphanumeric, 0 through 9, A through Z, all capital. I know that from the manual. I know there's a sync word, but I don't know how long it is, and I don't know what it is. And I know that there's some numerical data in there for the electrical resistance. So I don't know too much, but I know enough. It took me a couple days to get some things figured out. I don't have an oscilloscope. I had to borrow one. I borrowed a monstrous HP beast that was from '82. The manual, not real user-friendly. It took me a while to figure out how to do captures with it and to work with it. I also found the RF module was way too sensitive. I like to think of this as like when you were a kid, had walkie-talkies or a CB, you turn the squelch all the way down, it just made noise and it was, you couldn't hear anything. Same kind of thing. So I had some more register battles, but I got through it and I eventually captured 2 9-millisecond transmissions that were exactly 5 minutes apart. I'm thinking, awesome. So I collected a bunch more, decoded them on paper and pencil, and they look like total gibberish. This is not what I was expecting. I was expecting like TCP dump-like precision. I wanted to see these binary things line up and be always 76 bits and always perfect, and it would be very clear what it is. Not the case at all. So I was expecting, based upon my research, to have 8 bits of preamble. 10, 10, 10, 10, 10. What I saw was a series of 1s. I'm thinking, that's not what a preamble is. None of my research indicated that a preamble could be just a bunch of 1s. So I started to reread that data sheet, and they have something called RF sense. This is not a proprietary thing, but this is a different way of doing preamble that this chip manufacturer decided to do. It expects a wake-up transmission that's just a series of 1s instead of 1s and 0s. And when I decoded these packets, they would be anyway, I'd get 4 of them sometimes, I'd get 8 of them, 6 of them, And I'm thinking, oh, that makes sense, right? Because the RF thing's got to wake up from its power state mode. It's got to set the gains. And sometimes it's going to be slower. It's not always going to wake up the same speed every time. So that's why sometimes I get 4, sometimes I get 8. Okay, we're getting there. I got to think more like a cryptographer at this point, right? I know some of the plain text. I know the transmitter ID. In my case, it's CTA3. It's the last 4 of my transmitter. I know that most of the transmissions are identical every time, right? The sync word's going to be the same. The transmitter ID is going to be the same every time. I also know the data is not going to change a lot in 5 minutes. Even if I eat, an entire 2 liter, even if I drink an entire 2 liter of Mountain Dew, my blood sugar is not going to change that much in 5 minutes. So can I start to see patterns in the crypttext that'll kind of tell me where those things are? So I took 40 transmissions, and I made some rules. I said, I won't change any bits, but if I can move by 1 or 2 bits, do things start to line up? And they do. 80% of the transmissions out of the 40 I had the same first 24 bits right after the preamble. I'm like, that's pretty cool. But the problem is that when I transcribe them to actual characters, they don't equal a sync word, and they don't equal the transmitter ID. So I look at the data sheet, and it says it'll do a data inversion, which is basically instead of a 1, it's a 0, instead of a 0, it's a 1. So I do that, and I do all 40 transmissions, and I flip all the 1s to 0s and 0s to 1s. And then I decode it. And that didn't make any more sense either. That was still all gibberish. So you know what I'll do? I want to make sure I'm using this right. Let me talk to Texas Instruments. They made the chip. They'll know what to do. Clueless. They're like, direct mode? What's that? Oh, that chip does that? Yeah, I don't know what you're doing. That's when I started to figure out I was using this chip in a very obscure way. And I started telling them what I was doing. I said, well, I got this transmitter, and I don't know the format of the transmission, so I'm trying to figure out the format of the transmission. And they were like, I don't know if we should help you anymore. I said, why didn't you just ask the manufacturer? And then I was like, the chip's out of production. There's nobody available to answer that question. They quickly stopped talking to me after that. I never got a response from those emails. And that's about as far as I got with the CGM, right? There's just too many combinations of settings, and they all impact how that direct mode behaves, right? So I've got a bunch of data, and I can't really transcribe it. There's also no documentation on this. I had to experiment with all of this, all the register settings, the direct mode, all of it. There's also no user experiences. Even the chip manufacturer didn't have any experience doing it. They were no help. I was using this way beyond its intended purposes, which I felt really good about, because that's the definition of hacking, right? Is trying to bend it and make it do something it's not quite supposed to do, but will really, shed light on what you're trying to do, and that's how we learn. There's some security risks, though. I got around to playing with some things. The first one I tried is a replay attack. I don't know what the format is, but I can capture it, and I can replay it. So that's what I was doing. I would capture those values, and then I'd use another transmitter, and I would transmit those values back. I would just replay the packet as transmitted. And that really screwed my system up. It started to make a flat line, instead of which there's always a little variance in the data. So I knew it was receiving and decoding that transmission properly. But after a while, the CGM just gave up. It said, I don't think this is right. I want you to recalibrate. Which basically is, you kind of think of like a denial of service attack, right? You're rendering the CGM useless if you did that. There's some limitations, right? Physical range, the range of my transmitter, the range of the system is about 100 feet, right? But I've got an external antenna. I could do some modifications. At that bandwidth, at that band range, 400 megahertz, you could easily do quarter mile, half mile. I think that's within realistic expectations without too much craziness going on, without getting Pringle cans and satellite dishes involved, right? I also tried some denial of service stuff. I just keyed the transmitter, just let it send garbage. Because this little transmitter that I have attached to me in the legitimate system uses, basically nanowatts to transmit. So I'm clobbering the signal all the time. And what I got, the impact of that would be that I got no values to my CGM. The CGM is like, you must have taken the sensor off because I don't have anything for you. Again, same kind of deal. Physical range is a limitation. It's also not a critical function, right? The CGM provides you data. It doesn't, if it fails to work, meh. It doesn't, I would be like, oh, I got to do a blood test now. And this is first generation technology. It's pretty flaky. For it to stop working, we'll call it a common occurrence, but it occurs a lot. Where it just kind of flakes out for a couple hours and then starts to pick it up again. A potential security risk would be injection, right? If you can reverse the format of that transmission, you can construct your own sensor transmissions. So what you would do is listen and catch the transmitter ID, and then you would retransmit, you would transmit with with a spoofed ID, but you would fake the data portion, right? Now the impact of that's a little more severe, right? Because the user depends on that data for the insulin calculation. So if the user inputs the incorrect values into his or her equation, they might get too much or too little insulin, which, as I described before, can lead to all kinds of problems, especially in the case of having too much insulin. The limitations here are hard to overcome, which is human intelligence, that gut feeling. Every diabetic knows what it feels like to have low blood sugar or high blood sugar. They just know their body. When you live with it for that long, you know what that feels like. And many times I've looked at my CGM and went, you're lying. That is not my blood sugar. And it's wrong. I've seen it be over 150 points wrong. So that experience, when I look at it and I don't believe it, and I'll take a blood test to verify that, is what would happen, I think, here, right? Because you would see it, and you also, if it goes from 200 to 0, no, it didn't do that over 5 minutes, right? So that the human element there is going to prevent, is going to help people in that case. Another limitation is that I don't know the data format. I haven't decoded it yet. Maybe I will one day. Never know. Let's talk about the second technology. Insulin pumps, right? This is a medical device that delivers the insulin to you, and it does it in two ways, right? There's something called a basal insulin, which gives every 3 minutes. Think of it as kind of a baseline of the medication or the hormone in your system. And then it gives a larger dose at mealtime. Same kind of deal. You tell it how many carbohydrates, it does the math, calculations, it gives you the insulin. And it's delivered through tubing that attaches to your body. That tubing set is usually replaced every 3 days. So insulin pumps are used to deliver this to patients, and it's hooked to them 24/7, right? My insulin pump, sleep with it on, I take it off to shower and other special events. But most of the time, it stays on all the time. Now, there's some cool things that these pumps do, right? My blood meter, my glucose meter, sends measurements wirelessly to my insulin pump, right? And that makes it easier for the user, right? So instead of taking out my insulin pump and holding down the up arrow to get to 300, if that's my blood sugar, it just automatically, boom, shows up as 300. Excellent, right? There's also usually a USB dongle or a serial port dongle that I can plug in that allows me to program my insulin pump, right? Because there's a ton of settings. I could tell it what time, how much insulin, what my ratios are, do I want alarms, all these things. I can also download the data history. How much insulin did I give myself over the last week? And I can start to do data analysis with that with my doctor to make sure I'm doing all the right things. There's also wireless remotes for your insulin pumps, right? Sometimes at formal events, I'll wear the insulin pump in my sock because I have a suit that doesn't have any pockets. I don't want to get the tubing caught on things. And it'd be really inconvenient to have to lift my leg up, get into my sock, and give myself insulin. So what they make is they make little devices. For the manufacturer that I have, it looks like a car alarm remote. It's got 4 buttons on it, and you can give yourself insulin with this little remote control, all wirelessly. And this is kind of what a setup looks like, right? You can see the tubing that goes into the body. You can see the little plastic tube called a cannula that delivers that medication into your subcutaneous tissue. And you can see the insulin pump. It kind of looks like a little pager-like device. It's got some buttons on it so you can interact with it. It's my hypothesis here, right? Wireless communication with insulin pumps, I'm guessing, aren't secured. And they could be subject to attack, is my thinking, right? But I think communications are going to be a little more complex here, probably bidirectional. I don't have, it runs on a AAA battery that you could replace every couple weeks. So it can do more stuff. It can talk, it can do more transmissions, right? I also know that the computer programs used for the configurations are pretty ancient. In my case, my software won't install on anything other than XP. Crashes in Vista, crashes in 7. When you call the manufacturer and ask them about that, they say, we're not fixing that. Too bad. We're never going to fix it. It's not going to be updated. You have to live with it. Okay, that's interesting. Also kind of tells me a little bit of the mindset of the manufacturer. Maybe a little bit lack of knowledge on the computer side is what I'm thinking. Also, these devices are not designed to be updated. Like your phone, you can push a firmware update to. I've had my device for 5 years. It's never been patched. Right? There's no USB port on it. It's a waterproof device. It's very rugged. So having something where you can plug in to update firmware, I've never seen it done. And I don't know anybody who's ever done it. And these devices last anywhere from 5 to 10 years. And they're super expensive. They're about $6,000 for an insulin pump. All right? And insurance companies go through a lot of work with you to make sure you buy one insulin pump and use it for a really long time. The first place I went for recon here is that program that only runs in XP. Turns out it's a Java-based program. So I was like, I wonder what the log files would tell me. I go into the config settings. Logging is set to none. No, let's set it to high and see what it gives me. I get everything, right? Info. This is the command. This is the command I'm going to send, and the command sets the RF power on. I'm going to encode this packet. Then I'm going to write this packet out to the serial port. Well, I know the serial number format because I see my serial number up there, 313370. So I'm like, that's pretty easy. Look, there's a little CRC at the end. The command is 5A. There's my serial number. I'm like, this can't be that easy. And look, the encoding is kind of interesting. Right? It doesn't double the length of the packet, but it definitely makes it longer. And I'm like, I got to figure out this encoding. How can I do that? Well, I went to the jar file, and I said, I wonder if they obfuscated any of this. No, they didn't obfuscate any of it. So I decompile it. Conveniently, they give me all the commands for the insulin pump to allow me to do anything I want to do. Right? And it shows me the format in the comments of how I need to structure it, how the encoding works, how the decoding works, everything. So now I know all the commands and all the packet structure. So I start to think about this a little bit, and I'm like, okay, well, I know it talks to this serial port. There's a couple other ways it does it. It can do USB to serial, but I got this serial port dongle. And I'm like, the only piece of information I need to talk to this pump is the serial number? I think that's pretty lame. That's not too much of a hurdle to overcome. I start to think about this, and I'm like, I wonder what I can do with my pump to stop this. So it turns out I can't turn the RF, the wireless, off on my pump. It's on. It's always on, and it cannot be turned off. There's also no verification. If it gets a new configuration, it just accepts it. I don't say, it doesn't pop up and say, there's been a new configuration pushed to your insulin pump. Would you like to use it? Yes or no? It just takes it. The insulin pump does exactly what it's told without any questions. So I started to think about what other wireless things interact with the pump. Right? Those remote controls I talked about. Right? Turns out they all have a unique ID, a serial number. And the pump has to be configured to allow that serial number remote to talk and accept commands from it. The blood meter, it also has a unique ID, and it sends out a beacon with the value plus the ID, and that's how the pump picks that up. It looks for that ID and says, oh, I'm supposed to listen for that blood meter. I'm going to use that. Also, you can download all the historical data from it. So what do you need to do this? Well, the hardware you need are those little dongles, the serial adapter or the USB device. Turns out they're really easy to get your hands on. They're about $100 new. You can buy them directly from the manufacturer or a medical supply warehouse. And you can get them used on eBay for 20 bucks, 20, 30 bucks. There's no restrictions. You don't need a prescription. You don't need any special, special documentation to get them. They don't track them or anything like that. The remotes for the pumps, same thing. $100, $150 new. I've seen them go for $40 on eBay. Pretty trivial to acquire any of this hardware. What do you need to know to communicate with a pump? Well, you need the serial number. That could be probably socially engineered. Diabetics are pretty friendly. They like talking to other diabetics. If you go up to a diabetic and go, I'm thinking about getting an insulin pump. I see you have one on. Can I take a look at it? I just kind of want to see what kind of features it has. They'll probably just give it to you. You can look at it, 6-digit number. I can remember that. But you can also scan for it, right? If I know the command structure, I can say, hey, insulin pump 1, 2, 3, 4, 5. Are you out there? If I get no response, it's not out there. Like pinging a computer, though, if you say, hey, serial port 1, 2, or insulin pump 1, 2, 3, 4, 5, are you out there? It'll say, oh, yeah, I'm here. Ah, so we can write a scanner for it. That'd be neat. So here we go. Let's see if we can do a demonstration here of suspending a pump remotely. All right. Can you turn this camera on? Oh, I get to do that. That's right. It's upside down. Okay. So you can see on the screen here, there's nothing. And this is how the pump normally is. It conserves power. There's nothing on the screen. So now I'm going to run a command, or a little script that I wrote. And it's going to use this dongle that I have plugged in back here to communicate with my device. And I really hope this works. It works about 90% of the time. And what I'm expecting to happen is that the pump will vibrate once, and the screen will come on and say, suspended. Please work. I joke around that I sacrificed a lot of alcohol to the demo gods last night to make this work. There you go. So you can kind of see the impact of this, right? I can turn the pump off and stop delivery of insulin. It vibrates once. We have so many things in our pockets that vibrate and shake and whatever. I have totally forgotten that this thing has vibrated. I've missed it tons of times when it tries to notify me of something. What happens is that I figured out how to tell this dongle how to write. And when I tell it to write, it actually sends those hex characters that you saw out as binary on the wire. So if you know how to construct the packet, you basically tell the serial port, write this, and it transmits it out. And then you say, listen for a response. It is RF. There's nothing connected. This is the little RF dongle. There's no wires or anything that attaches to this. So I did it remotely with the RF. This little thing's got like a little paperclip antenna, and it doesn't go very far at all. What other things could we do now? Did it change? No. There we go. What are the security risks other than turning it off am I worried about? Well, the first one that makes probably the most sense to everybody would be full remote control, right? I can tell the pump to allow my remote, number 1, 2, 3, 4, 5, to accept commands. right? And the impact of that would be full insulin delivery control. So if if an evil hacker hacked my pump in the crowd here and told my pump, accept commands from my bad guy remote, he could give me insulin right now without my authority. All right? The limitation of that is, again, physical range, 100 feet. If you got one with an external antenna, you could probably get a lot more. Like I said, quarter to a half mile. Also, the pump notifies you of a delivery. That's not going to do you a whole lot of good after you're like, oh, why? Oh, I just got 10 units of insulin. Who did that to me? Right? This is scary because, like I said, you can't take the insulin out. So now I got to go find some Mountain Dew to cover the insulin that some jerk hacker just gave me. Right? But this applies to every configurable setting on an insulin pump. Right? I can manipulate all the ratio data. I can manipulate any setting on the insulin pump. And I do it, unlike that, when I do it, it's stealth. The pump doesn't react at all. So when I set the remote ID, which I've done, it does nothing. That's even scarier. Because in this case, and that's why I didn't demo it, because I'd be like, see, look, I changed it. And you'd be like, it didn't do anything. Like, aha! Right? So it's basically like having root on the device. And that's basically like having root in the chemistry of your body. It's not good. What are future scary things? What are they doing with this technology? What's the future? Well, the Juvenile Diabetes Research Foundation has a big project called the Artificial Pancreas Project. What that's going to do is it's going to link the CGM devices and the insulin pump together. So that way, the insulin pump doesn't have to bother the user to tell it what blood sugar is. It's going to eliminate the user. It'll just act on the data. Why do we need users? The CGM data, so if it's CGM data shows that your blood sugar is too low, the insulin pump will shut off. If it's too high, it'll give you more insulin. This makes the secured transmission of those CGMs much more important. Now there is no human gut feeling there. We've got to think about how those technologies talk to each other in a secure way, because it's going to be used to automate the process of insulin delivery. Also, next generation devices are using a new RF range with Bluetooth, right? There are a couple new pumps that have come out that have CGMs, and they're partnering with CGM companies with the insulin pump so they can have new features. Now, is this better or is this worse, right? Maybe both. Because Bluetooth has all these tools that you can use for hacking. We've done stuff with that, right? We've seen presentations on what bad things you can do with Bluetooth, right? There's tools for exploits. But there are also some security features built in there. I'm petrified to think of like a Metasploit module for medical devices or insulin pumps. That's really scary. What are my suggestions? So if you're a pump manufacturer in the crowd, I would like you to use these RF chips that have crypto built in. Turn it on. Please use it. Right? Don't make it so easy to sniff these transmissions or look at these transmissions that are not encrypted. All right? I also suggest using infrared rather than RF. I've had insulin pumps that use infrared technology, and you can disable them with a piece of tape. It is a pain in the ass to use those. You've got to line them up, and they're only 5 feet in range, and they're slow, but they're not hackable, and you can turn it off. RF, in this pump, you can't turn it off. A lot more range. You got to think about that. And you should do some simple things, like maybe a verification step, so that way a user has to verify that a new config is at their pump. You also have to maybe set a passcode, right? If you give it a PIN, I know it's not the most secure thing in the world, but it's better than just having the serial number I can scan for. I also think that companies should keep in mind range of transmission. One pump manufacturer uses 13 megahertz, which I was shocked to see, right? That's really an obscure frequency, and it's also really close to the 20-meter ham radio band, which is pretty infamous for having 1-watt communications that go globally. So now I'm thinking, Well, I could modify some ham radio equipment, and I could start attacking pumps from across the country, on the other side of the world, maybe. Interesting. Also seen good research on blocking technology, right? You saw probably some of the pacemaker research that's been done where you can wear a necklace that'll stop RF radiation from getting to that pacemaker. That's good work. We could see that used in medical devices more, I think, especially with more wireless capacity with those medical devices. How does this apply to other worlds? How does this research, is this research just for medical devices? I talked a little bit about SCADA. I found that these chips are used in SCADA environments, right? Older SCADA wireless systems use these chips, these on-off keying wireless chips in the sub-1 gigahertz range. So you can use the same techniques, the same hardware to look at different targets, to look at different research, right? And the thing about those devices are, they're in the field for a lot longer, right? You think of a water pipeline, a chemical pipeline, they're harder to replace. They might not even exist anymore, and they're more costly to replace, right? If you got to replace 100,000 of them, that's a big cost, right? And they're designed to be there for the life of the pipeline, right? Not a year. So you're looking at, oh, I got to have something that's going to last 10 years, 20 years. And that's hard to do. Overall, what did I learn with this little venture out into hardware hacking? It's a huge value. I think more of it should be done, and I'm excited to see presentations at Black Hat and DEF CON that dive into that, right? Because everything is becoming wireless and connected. Everything has an embedded processor, an embedded controller in it. So we've got to start looking at that because there's always a threat lurking, right? We can't just ignore it to think that it's an insulin pump. Nobody's going to hack that, you know? Well, that's what we said 15 years ago about the web. Who's going to use the web? For what, like shopping and banking? Are you kidding me? Oh, we are. Oh, we're using something that wasn't designed to be secure? Oops. So, you know, we need to look ahead of the curve now, right? Just because it can't be done easily, this can't be done easily, but it doesn't mean that we shouldn't look at it. And don't hide behind obscurity, right? I called this particular manufacturer my pump, and I said, hey, you guys produce this little RF thing that comes with the pump. You got like a software development kit for it, or maybe some codes that I can use? Because I'm thinking about writing a piece of software to download the data from it. And they were like, that's proprietary, sir. Click. So there are way too many smart people out there. Every time you try and hide behind obscurity, it fails. It's going to fail. You need to look at security first. You need to design it with security in mind. The other thing that I found out about hardware hacking is it is hard, right? We take for granted all the tools that we have when we do other security research, TCP dump, Wireshark, all of these things that make it easy to do our work, right? Think about trying to transcribe TCP packets on an oscilloscope. It's hard. It's a hard concept. It's a lot of work, you know? More tools are needed, more interest is needed to kind of develop the framework of tools, to develop those things that will help us with hardware hacking. I want to remind everybody to complete their feedback form. If you have any questions or comments, here's my email address, my Twitter handle. Thank you very much for coming to the presentation.